Picking up where we left off, I wanted to mention a few things. I know I circled this temperature in the last slide, but I don't think I did a very good job of explaining it in the last video. I was kind of tired, I apologize. But what we have here in this first one is we have a primary alcohol. Here we have a secondary alcohol, and here we have a tertiary alcohol. This primary alcohol requires 180 degrees in order to form this double bond. And this tertiary alcohol only requires 50 degrees to form this double bond. There's actually kind of a range of temperatures. I remember I said somewhere between these you might get difference. Well, it depends on what we start with. So if we start with a primary alcohol and we have 170 to 180 degrees, we'll get an alkene. Secondary, 100 to 140, we'll get an alkene. And tertiary needs to be 25 to 80 degrees to get an alkene. Now we see that secondary, we have 140, and we're getting the diethyl ether product. That is going to happen if we usually don't have high enough temperatures. And we'll discuss this in a moment. So I'm going to let you stay with starting with these temperatures, what we're going to get for the alkenes, but let's talk about why. So there are two different types of this type of reaction that this alcohol is undergoing. So dehydration is an example of what we call an elimination reaction. Now, elimination reactions are where we're going to get rid of two groups or two atoms that are on neighboring carbons, and they're going to be eliminated or removed. In this case, it's going to be an OH and an H forming water, which is why it's dehydration. Primary are the most difficult to undergo because they undergo what's known as an E2 or an elimination type 2 reaction, which is a one-step process. The reaction has no unstable carbocation intermediate, but it's difficult for those primary ones to undergo. Secondary and tertiary alcohols are going to undergo what's known as an E1, which is a two-step elimination process. Because it happens in two steps, they're going to form that unstable intermediate, but the tertiary carbocation is much more stable than the secondary or primary carbocation for that matter, so it doesn't require as much heat. So that's where these temperatures are going to be giving us that different product. So primary, secondary, tertiary matter, and the mechanism for this is going to be for the E1, so this is our two-step process. So we're starting with a secondary or tertiary alcohol. The R group here can be a hydrogen, but because this one cannot and this one is not. Okay? So here we have our strong acid. Strong acids ionize in solution, meaning that they're going to break this bond, give the electrons to A, forming a hydrogen ion and A minus. And then these electrons here on the oxygen are attracted to the positive side here, where the hydrogen has no electrons, and we get this protonated alcohol group. And this is the conjugated base, if you remember that from acid-base conjugate pairs, which is the Bronsted-Lowry acid-base pairs. Now, this protonated alcohol is going to lose that molecule of water. So we're going to give away, this is called the leaving group, this water as a leaving group. This is actually the slowest step, the rate determining step here. And we're going to leave this carbon with the carbocation here. Now, if R is a hydrogen and we have a secondary carbocation, it's going to be harder, or it's not going to be as stable as the tertiary one, but remember carbocations aren't stable anyway, so they're still both unstable. Once that happens, the A that was in solution, our conjugate base, is going to come back. The electrons that it has are going to grab a hydrogen from the nearby carbon, and that hydrogen is going to donate its electrons back, forming that double bond. And that is how the process goes. Now, you do not have to know mechanisms for this class. You don't have to draw them out, but sometimes it does make more sense. We're going to move on to the next reaction, which is going to be oxidation. Oxidation of primary or secondary alcohols. So why just primary and secondary? Well, you need to have a hydrogen on the carbon that we're removing it from, so you must have that in order to undergo oxidation, so we can't do that with tertiary, and I'll explain that more in a minute. But generally, what we're going to look at here is we're going to add oxygen or remove hydrogen to get a double bonded oxygen, and then that carbon atom that had the OH group is now going to have a double bond, a carbonyl group, whether it's a terminal and it's an aldehyde, or it's in the middle and it's a ketone. But these aldehydes that are formed are going to be extremely reactive and form what's known as a carboxylic acid. So the terminal, we have our R group, C double bond O, H. This is actually going to react to become C double bond O, OH with our R group. And the ketone is going to be somewhere in the middle. All of our secondary alcohols are going to become ketones. There's no other option for those. There are a couple different types of reagents we use. Generally, the most useful reagents for oxidizing primary and secondary alcohols are going to be some type of chromic acid derivative. So two examples of these are the Jones reagent and pyridinium chlorochromate. So Jones reagent is actually a solution of sodium dichromate, and it's in aqueous sulfuric acid. And then we have pyridinium chlorochromate, which is usually given the acronym PCC. Sometimes you might see PDC as well, but PCC is probably what I'm going to use. It'll be most common here. And it's usually in a methylene chloride solution, so you might see Cl2. So you might see those written there as well as part of what's in the solution. Now for both of these reagents, no matter which of these reagents we use, we're going to get some type of intermediate. It's most likely is going to be some type of chromate ester. And the chromate ester of the alcohol substrate is then going to undergo some type of E2-like reaction. So some type of second type 2 elimination type reaction and give a carbonyl product. So we're going to get this product. Now, these are all redox reactions. So the oxidation state for carbon is going to increase by 2, and the oxidation state for chromium is going to decrease by 3. That's important because it does actually give a color change. So the oxidation state of chromium goes from 6+ to 3+. It's reduced. And when it does that, this one is normally in orange-red color, and the chromium 3 product is generally a green color. And that color change allows us to see the reaction taking place. It's a visual transition. It's actually the chemical transformation in which they've based the breathalyzer test to see if you've been drinking while you're driving. So this is going to be visual, something that you can see happening. Let me just be clear. I'm going to erase this. I want to be clear about what we get here. So with Jones reagents, if we have a primary alcohol, are going to go all the way to the carboxylic acid. They stop briefly at the aldehyde in the middle. If you have a secondary alcohol, no matter what you use, you're going to get a ketone. Now with PCC, you have a better chance, can't spell today, chance of seeing the aldehyde for longer. So PCC isn't the only one we could use. There's another one, but also doing these under cold conditions. So you could see also written CrO3 with pyridine and saying it's cold. The cold is going to help slow down that reaction of the aldehyde going to the carboxylic acid, but remember, this isn't going to stick around very long. Eventually, it's all going to go to the carboxylic acid. But if I give you the reagent PCC, I want to see the aldehyde product. If I give you the Jones reagent, I want to see the carboxylic acid product. So I know that you understand that there's a reason that we use different reagents at different times. There are two structural requirements for the oxidation to carbonyl products. Again, the carbon that's bonded to the oxygen must also have a hydrogen. This is why tertiary alcohols cannot oxidize in this way. They must have a hydrogen. Oh, whoops. So if they must have a hydrogen, and tertiary alcohols do not have a hydrogen, so they can't undergo this type of oxidation. The oxygen atom must also be bonded to a hydrogen atom so that a chromate ester intermediate or some other type of leaving group that's suitable. If you don't have a good leaving group, the reaction won't happen. Now, we don't talk a lot about leaving groups in this course, but if you take a full semester organic class, you'll hear a lot more about those. So ethers, this is why ethers cannot be oxidized in this way. So let's take a look what we're actually doing here. We're going to take this red OH group and we're going to turn that into, and get rid of this hydrogen as well, we're going to turn that into a carbonyl group that's known as oxidation. But we can also come back, which we'll learn about later, when we take this carbonyl group and we can add hydrogen to it and reduce it back to an alcohol. So in your food, you might try to avoid sugar or something like that. You might see sugar alcohols. And what they do is they reduce the aldehyde or the ketone back down to an alcohol, and your body doesn't recognize it as an actual sugar anymore. But that also comes with digestive problems, gas and bloating and diarrhea. So they do manipulate our food in this way to try to make it, I don't know, just depends on what you're looking for in your food. But that's just one example of that. Let's look at some reactions. So oxidation, primary alcohols, depends on the reagent, right? Jones or any of these other reagents are going to get carboxylic acids. PCC, chromium and pyridine, if under cold conditions, will get an aldehyde. So if I say let's react it with KMNO4, or we can see the chromate reactions down here, will give us the carboxylic acid. But if I were to say let's react this with pyridine and cold, or if we had PCC written there, you would get the aldehyde. But remember, this aldehyde is brief. It's going to oxidize easily to the carboxylic acid. So on a question like this, I might say, show me the final product, or I might say, show me both, both reactions, or something like that. Yeah, the wording might be kind of different. I'll try to give us some practice. Secondary alcohols, it does not matter what reagent we use. No matter what reagent we use, we're always going to get a ketone. We're losing two hydrogens. The usual oxidizing agent is some type of chromium-6 species. So here we have CrO3 and pyridine. So here we saw that one in the last one with it was cold and we would got the aldehyde. There's no possibility of getting an aldehyde here. Because it's in the chain, we're going to have to get that doubly bonded oxygen, and it's going to be centralized on the chain. So we're going to have that ketone. So we're going to always get a ketone from a secondary alcohol. Now, if we were to take a look at tertiary alcohols, this is what we're saying, that tertiary alcohols we're going to get. It doesn't mean I won't ask you just because there's no reaction. Because they lack that necessary hydrogen, this would give us this particular product. What's wrong with that? What's wrong with that structure? Take a minute, pause it, and look. 1, 2, 3, 4, 5. Don't forget the most basic rule of this class. Carbon has 4 bonds max. So count those bonds. We would end up with 5, which is not possible in what we're discussing to have to carbon. Practice. This means pause it and try it. Okay, so pause it. What is my product going to be with PCC? What is my product going to be with any other? This is any general oxidizing agent. So that just stands for like any oxidizing agent. So what will we get with this one here? We're going to get the aldehyde, at least briefly. And down at the bottom, we're going to get the carboxylic acid. All right, more practice. Pause it and try it. Here we have a secondary alcohol. Doesn't matter what the reagent is, we're going to get the ketone. And here we have a tertiary alcohol, which would give us no reaction. All right, so moving on, be careful. Remember that this is the reaction that they use for breathalyzers, is going to be this reaction with the chromium compound, so we can see it change color. And they actually pick up a percentage, and at least that's what it's based on. Now, other things that ethanol can do, I do like to do a couple of public service announcements whenever possible, or, what are you guys going to see? Most of you are going into some type of healthcare usually, so let's talk about what you're going to see. So fetal alcohol syndrome, why shouldn't people drink when they're pregnant? Other countries, maybe they have a glass of wine or a beer, but how much is too much is usually a study that most women who are pregnant don't want to sign up for. So unless someone has been abusing alcohol, usually we don't find out how much is too much. So what happens when a fetus has been exposed to alcohol? They actually lack the enzyme that's necessary to break down ethanol, and ethanol passes through the placental membrane. So it does affect their ability to process the alcohol. There's a syndrome called fetal alcohol syndrome, FAS, and it's a group of signs or symptoms that appear as a result of somebody drinking while they were pregnant. So you might see a flattened upper lip, you might see like lowered ears. What are some of the other ones? So just a few, maybe the ears are lower, like I said, the upper lip is flattened, it doesn't have the little thing that comes down the middle. But these are just some facial features of fetal alcohol syndrome. And what is actually happening chemically is that this alcohol dehydrogenase, which would normally break down the alcohol and get rid of it, they don't have it, so they can't do that, and it's going to affect their growth. So, what is I'm trying to think of some of the other facial features, maybe an upturned nose. What are something with the eyes? Man, I'm really struggling today. I guess I should have looked it up again before I started talking about it, but oh well. So anyway, these are some things that you might come across if you're working in the field that you can look at and see. Anyway, I'm going to move on. These are some of the reactions that we discussed. So this is just a little review slide that you can look at and see how you're doing and where you're at. Moving on to ethers. Remember, with ethers, we have an R group on ether side of the oxygen, and they're slightly polar because of this oxygen group. So oxygen has an electronegativity of 3.5 and carbon of 2.5, I think? Yeah, I think so, because hydrogen's 2.1. But they don't hydrogen bond to one another because, remember, in order to have a hydrogen bond, you have to have hydrogen directly bonded to the oxygen. So since we don't have that, we don't have hydrogen bonds forming. But they do have dipole-dipole interactions, which are going to increase the boiling point, but they're going to be lower than alcohols because they don't have the hydrogen bonds. But they're higher than alkanes because they do have dipole-dipole. Small ethers are going to be soluble in water due to the dipole-dipole interactions, but they're going to be not as soluble as are alcohols. So ethers are very unreactive, so they're useful as solvents. Diethyl ether was originally used as an anesthetic. However, it is flammable, which is not something you want to have, especially since oxygen is an oxidizer. And when you have flammable compounds and oxidizers mixed together, that's called a flamox mixture. And you don't want to have those together because if they're together in a pressurized container, that's called a bomb. So we don't really want to do that. We don't want our patients starting on fire. So we've now gone to different types of anesthetics that are not as flammable. But like this is a halothane they call them. But we put some halogens on there and this makes it less flammable, but still commonly can be used as an anesthetic. So it can give the same outcome. There are still many uses as ethers today, from cocaine production to diesel engine fluids. So we have a lot of uses for them. Not all good, but take the good with the bad, right? All right, let's learn how to name them. So the name of there's two groups attached to the oxygen, right? An R group on either side. We list them in alphabetical order, followed by the word ether is the common name. So you'll have seen me do this. I'll say dimethyl ether, diethyl ether. This one is methyl, and there's a, what kind of group is that? It makes that Y with three carbons. So we have a methyl group, and we have an isopropyl. So we would list them in alphabetical order. Alphabetical order is always correct, but in this case, you could also list them in size order. So we could say methyl isopropyl ether, because we say this is actually size order. But would isopropyl methyl ether be okay? Do we look at the I for iso or the P for propyl and the M? What's our alphabet again? A, B, C. So we haven't gotten to M yet. I comes before M. So isopropyl methyl ether is also appropriate as a name. Here we have benzene, or as it's a substituent, it's called a phenol. And we have ether, or sorry, ethane. It is an ether as well. But we have ethyl because it's a substituent. So we're naming these as substituents. E comes before P, as well as in size order and in alphabetical order. This would be ethyl phenyl ether. I would say always go with ABC order because it's always right in many of the different things that we do, versus size order. It can be appropriate here, but it's not always correct. So why not just pick the one that's always correct if you're going to learn it? IUPAC names are based on the alkane name of the longest carbon chain. So we're still going to find that longest carbon chain, and we're going to name the other chain, the shorter chain, as an alkoxy. That means the alkane name, but change the ending to oxy as a substituent. So the longest chain here is 1, 2, 3, 4, 5 carbons. So it's a pentane, but we have a methoxy group. So methane, we drop the ane and change it to oxy. So methoxy. All right, practice then. Let's find out what these names are. Here we have two ethyl groups. Common name, diethyl ether. But I want the IUPAC name, so the IUPAC name would be ethoxyethane. Over here I have cyclohexyl and I have methyl. So this would be cyclohexyl comes first before methyl. So it'd be cyclohexyl methyl ether. But the IUPAC name would be 1-methoxy. You don't really need the 1 either. Cyclohexane. And I just noticed that it was above what I'm writing. So we don't actually need the 1 because there's only one substituent on the cyclohexane. All right. Go ahead and pause it and practice and try to come up with your answer. Pause it. Okay, we have propane. Propane is the longest. So that's our parent chain. This is methyl. So we have methoxy, 1-methoxy propane. Yes, you need the number there. Here we have a double bond and no double bond. So because this is going to have the double bond in it, it's going to be our parent chain. So this will be ethene, and this will be ethoxy. We don't really need a number here. So ethoxyethene. And here we have 1, 2, 3. We have 3 methoxy groups at 1, 2, 3, 4, 5, and 6. So 1, 3, and 5. 1, 3, 5. Trimethoxy benzene. Same rules as before, just changing the endings differently. What reactions do ethers undergo? Well, remember we said ethers are pretty moderate. They don't react very easily, but symmetrical ethers can be prepared by dehydrating 2 alcohols. We just saw that a moment ago. It has to be at a lower temperature. So the lower temperatures with acid and a little bit of heat, we're going to get symmetrical ethers. So I'm not going to stay in detail with this. We're not going to practice it because we already did in this chapter. Next up, we're going to briefly talk about phenols again, but since we already talked about phenols in the last chapter, we're going to just kind of review it a little bit quickly. Phenols are alcohols that have a hydroxyl group attached to a benzene ring. So this is our benzene ring, which makes it special and different. So what is going to happen is a lot of the electron density, I don't know why that keeps happening, but a lot of the electron density from the OH group is actually getting pulled toward the ring, which makes this hydrogen easier to remove. Now, normally, we don't talk about alcohols being acidic at all in this class because they really aren't very acidic. But when they're attached to this benzene ring, again, we pull that electron density away and that hydrogen can be more easily lost. So we can undergo some an acid-base reaction. So they're going to be more acidic because they can have that resonance stabilization with the anion. But these are useful in certain ways as antiseptics, flavorers, and preservatives. So we can see some of them, we talked about them, but we didn't talk about what they were for. But phenols are used as germicides, flavors, and preservatives. We went over quite a few of them in the last, the benzene and derivatives chapter. But this is thymol. It becomes mint or thyme. Lysol. This is what's paracresol, which is cleaning and killing all the bacteria. Hexylresorcinol. This is a sore throat anesthetic. And urushiol, which is the one I hate, from poison ivy, poison oak. This is what's causing the actual reaction. Notice why you should not just wash with water, because water is just going to spread this around your body because this is nonpolar here. I get that it has these 2 H groups. That's great, but there are 14, 15, 16 carbons on that chain on that, and it's going to just spread it around your body. So Dawn dish soap, alcohol, you're definitely going to want to mix those in a solution. Plus they have other things that you can use now on the market, but if you have a chance, just stay away. This is a good one. It's been brought up. It's now legal in Michigan. This is vitamins T, H, and C. So vitamin A, vitamin B, vitamin THC. This is tetrahydrocannabinol. This is what's in cannabis that people like so much. So we have a phenol here, a cycloalkene, and a cyclic ether that are in these compounds. So the reaction I was mentioning that has this possible acid base, if we react it with a base, it can act as an acid and we can form this salt. It's called a salt because we're reacting it an acid. The product of an acid-base reaction is always water and a salt. Now it's not just table salt, the sodium chloride. This is called a salt because it's the cation from a base and the anion from an acid. So alcohols in general are not acidic, but the phenol is slightly acidic, so we can undergo that reaction. Thiols. Thiols are really stinky. Yes, Mr. Skunk here. You smell bad. I actually had a bike ride past a skunk smell the other day. It was pretty nasty. All right. They are slightly polar, but not so much. They can't hydrogen bond. Very, very, very smelly. And the skunk smell, what you're smelling is 3-methylbutane thiol. So that is actually what you're smelling coming from Mr. Skunk. Let's name some thiols. All right, naming is based on the longest continuous chain containing that SH group, that thiol group. So here we go. That's our longest chain. It contains the thiol group. 1, 2, 3, 4 carbons with a methyl group attached. but we're going to start counting on the right-hand side. 1, 2, 3, 4. We have a methyl group, and then our thiol. So we actually just add the suffix thiol. So in this case, we have butane. We don't drop anything, we just say butane thiol, and then we add the prefixes for the substituents out front. So what is this? It's going to be 3-methyl 1. We do need to number the thiol because it doesn't have to be terminal. So 3-methyl 1-butane thiol. Oops, I'll go back for a second there. All right, pretty simple. So we just add the ending thiol. Reactions for thiols. We don't have a ton of reactions, but this one is a very important reaction. You're going to see this again. So this is a thiol group, and this is a thiol group, and when we oxidize them, we get what's known as a disulfide. You may have heard of those when you're talking about biology. We talk about disulfide bonds and folding of our proteins. Yes, it is extremely important because we have this one here, cysteine. We have cysteine, which has a thiol group on it. And when two cysteines come close together and we have an oxidation take place, we form a disulfide bridge. This is a critical factor in protein folding and structure. So we really need to pay attention to this. It is important. Do you have curly hair versus straight hair? When you try to change it from one to the other, you're going to be breaking these disulfide bonds and then reforming them in a different way. So this is actually showing you two different chains. We have an A chain and a B chain of this this is actually insulin. So you can actually see them folding back on themselves by forming these disulfide bridges here. So that's what's going to cause the kinks in the chain and allow them to stay attracted to one another. So this is insulin. This is preproinsulin. Okay. Now, some other mentions of what's going on, because again, you're going into healthcare, so I like to try to bring up some of the things where healthcare workers were extremely important and vital. In 2014, Flint, Michigan switched to source from the Detroit water system to the Flint River. Well, it wouldn't be a big deal, but the Flint River was corrosive and it caused the lead from the aging pipes to leach into the water supply. This is a problem. Lead poisoning is a real thing. Now, my only problem with the Flint water crisis is what they don't tell you is this happens all over the place in any old city. So New York, Chicago, downtown Detroit, because even if they replace the pipes that are in the water system, which Flint is still dealing with today, people have to replace. So if this is the street and your house is here, people have to pay to replace the pipes that go from the street to their house. So if they're in an older home, they can be getting lead poisoning from these pipes and the pipes that are in their home, and this happens. So we don't often focus on why we have lower, IQs or anything like that in children with school, because we don't in these bigger cities, because we're already having a lot of times a hard time with the school systems there, and we don't catch this all the time. So 6,000 and 12,000 children have been exposed to drinking water with high levels of lead, and they can experience a range of health problems. Well, what's happening? So in this thiol group that's supposed to react, the lead interferes with the proteins. So the lead comes in, interferes with this disulfide bond, and it's not folding properly anymore. So these genes that are supposed to turn on and off by displacing other metals in the molecules, it actually changes the whole shape of the protein and it can't perform its function. So now if we don't have proper shape, we don't have proper function and folding of a protein, they cannot react or they cannot do what they're supposed to do. These are just some of the symptoms that people noticed of kids, adults even coming into the ER. So it was healthcare workers that were leading the fight in this particular crisis, saying, no, we have a citywide problem here. We have a problem, and we have to get people to listen to us. So this is what people were seeing. And just so you know, you can make a difference. So you will make a difference, and just keep fighting a good fight. I'll see you guys in the next chapter.